Hi everyone, once again welcome back to the finite element analysis of beam session 6, where in this session we are going to solve the problem number 3. And so learning outcome for this session is to solve the given problem. Now this is the problem. A propped cantilever beam is loaded as shown in the figure below. So this is the propped cantilever beam with two roller supports. Now for this problem we need to find out the deflection and slope, then moment and shear force, deflection at the midspan in each portion of the beam. Then finally we need to find out the reaction at the fixed supports. Take E is equal to 2 into 10 to the power of 5 Newton per mm square, and moment of inertia is 5 into 10 to the power of 6 mm raised to 4. Now start with the FEM solution. Now first we need to do the FEM model. So here we need to consider the two beam elements, because this is the beam element which is subjected to two different UDL loads. So one is 12 kilonewton per meter, another one is 24 kilonewton per meter. Therefore we are going to consider the two elements here of 5 meter length of each element. Then the possible application of displacement and forces I have shown at the each node. So this is node number 1, node number 2, node number 3. Like V1, V2, V3 are the vertical displacement. Theta 1, theta 2, theta 3 are the slope which are there at node number 1, 2, 3 respectively. So this is what the FA model. Now once the FA model is done, next we need to do the calculation of element stiffness matrix. So before doing that, let us convert or let us make all the units uniformity. I value I given in terms of mm raised to 4. So but applied load and lengths are in terms of meters. So let us convert that also in terms of meter. Therefore I will become 4 into 10 to the power of minus 6 meter raised to 4. The next modulus I have given once again Newton per mm square. So let us that also we can convert in terms of Newton per meter square. So it will be 2 into 10 to the power of 11 Newton per meter square. So after this, so this is what my second step, where I need to find out the element stiffness matrix. So to find out the element stiffness matrix, so I need to consider the element stiffness matrix. So element stiffness matrix for beam element is given with this. Then substituting all the values of E and length of first element. So my length of the first element is 5 meter. So I'll substitute all the values in terms of meter. Then inside the matrix, wherever length of the element, there also I'll substitute 5. Then after simplification, this outside constant is 8 into 10 to the power of 3. Then the value which is inside the matrix is this. And the first element is subjected with the 4 displacement, that is 1, 2, 3, 4 vertically, and 1, 2, 3, 4 horizontally I mentioned here. Similarly, I need to find out the K2, but as my second element is also having the same Young's modulus, moment of inertia as well as length. Therefore, my K1 is equal to K2. But the 4 displacement associated with the second element is 3, 4, 5, 6. So that is what I mentioned horizontally, vertically. So that number will help in the next step, that is third step, doing the global stiffness matrix. While doing the global stiffness matrix, those numbers will help out. So once again I have 6 degrees of freedom, because at each node I have 2 degrees of freedom, totally 3 nodes, therefore I'll get 6 degrees of freedom. Therefore my global stiffness matrix is a 6 cross 6 matrix. So where I need to get the global stiffness matrix by adding the K1 and K2. Once again here I have 3 of 3 2 values. From first matrix 3 of 3 is 12, from second matrix 3 of 3 is 12. Therefore wherever 3 of 3 comes in global stiffness matrix, there will get the value of 24. Similarly 4 of 4 I have two values, that is 100, and 4 of 4 it is 100. So wherever 4 of 4 value comes, there I'll get the value as 200. Remaining will read as it is. So 1 of 1 it is 12, 2 of 1 it is 30. So like that you are go on writing. But where 3 of 3 comes, as I told, it is 24. Similarly 4 of 4 when it comes, it is 200. Remaining all the values which are there from K1 and K2. And of course from both the K1 and K2 matrix, 8 into 10 to the power of 3, which is a common term, which is kept outside of the matrix as it is. Then here this is a problem where it is subjected to the UDL force. Therefore I need to convert that applied UDL force into equivalent nodal forces. So let us convert first UDL, that is 12 kilonewton per meter, which is applied on the first element. So the conversion of UDL into point load, we know that it is q naught into L divided by 2 on both the nodes, that is vertical force. Then q naught into L square divided by 12, those are the moments which are applied at node number 1 and 2, where moment applied at node number 1 is negative and moment applied at node number 2 is a positive value. Now let us put the values of q naught and Le. So for the first element, the value of q naught is 12. It is in kilonewton per meter. Therefore, convert it in terms of Newton. Length is 5 meter divided by 2 as it is. So after calculating, I am going to get it as a minus 30 into 10 to the power of 3 Newton. Similarly, I need to calculate m1 and m2, but here f1 is equal to f2 because both are negative values. So it is minus 30 into 10 to the power of 3 Newton. So next I need to calculate m1 and m2. Once again, m1 and m2 both values are same, but they are opposite in sign. So m1 is minus 25 into 10 to the power of 3 and m2 is plus 25 into 10 to the power of 3. Same substitution applied. UDL is 12 kilonewton per meter. Therefore, it is 12 into 10 to the power of 3 Newton per meter, and length is 5 meter for first element. Therefore, it is 5 square. So minus 25 for m1 plus 25, that is kilonewton meter. Therefore, I multiplied with 10 to the power of 3. Therefore, it is minus 25 into 10 to the power of 3 Newton meter. So next I need to do the same thing for the second element. So there my second element is applied with a force of UDL force of 24 kilonewton per meter. Therefore, once again the conversion of UDL into point force is same thing. Then substituting the values of 24 into 10 to the power of 3 into 5. Once again the length of the second element is also 5 meter. So like that I will get F2 and F3. So these are the two forces which are there at node number 2 and 3. Therefore, it is F2 F3 is equal to minus 16 to 10 to the power of 3 Newton. Similarly, when I substitute in terms of M2 and M3, that is M2 is there at node number 2 and M3 is there at node number 3. Therefore, M2 and M3 both are of same value but opposite in sign. So M2 is minus 15 to 10 to the power of 3 Newton meter. Same thing by substituting the value of UDL of 24 kilonewton per meter, and in M3 while calculating M3 also the Q0 value is 24 into 10 to the power of 3, where length is 5 meter, where square is there. We are going to apply the square. After solving this, I'll get minus 15 to 10 to the power of 3 Newton meter for M2 and plus 15 to 10 to the power of 3 Newton meter for M3. Now next I need to calculate the global force vector. So because I have two different forces I calculated after converting UDL into point forces, I need to club together to get the global force vector. Let us put the force vector for the first element. So F1, M1, F2, M2, these are the four forces applied with the, subjected with the first element. So F1, M1, F2, M2 we have calculated for the first element, which is minus 30, minus 25, minus 30, plus 25. Anyhow, the same, the four displacement associated with the first element is 1, 2, 3, 4. Similarly, we need to calculate the force matrix F2 for the second element. That is given by F2, M2, F3, M3, which is minus 60, minus 50, minus 60, plus 50. Then I need to club these two to get my global force vector, which is a 1 cross 6 matrix, because I have a 6 forces applied at all the 3 nodes. Therefore, my total global force vector is F is equal to F1 plus F2. So that is F1, M1, F2, M2, F3, M3. So where I'll get adding the two values of F2, because I have two values of F2, minus 30, minus 60, it will become minus 90. Similarly, I will be having the two values of M2, that is plus 25 and minus 50. So it will be minus 25. So the value of M2 is minus 25, remaining minus 30, minus 25 for F1, M1 as it is, and minus 60 plus 60 for F3, M3 as it is. So this is what my global global force vector. So in the next, we need to put everything in the form of equilibrium equation and applying the elimination method of boundary condition. So this is my global stiffness matrix multiplied by displacement matrix, where V1 theta 1, V2 theta 2, V3 theta 3 is my displacement matrix, that will be equal to the force matrix. Then applying the elimination method of boundary condition, wherever there is a boundary condition, there the displacement we need to make it 0. As my node number 1 is completely constant, my V1 and theta 1 will be equal to 0, and my node number 2 is applied with the roller support, therefore V2 is equal to 0. Similarly, node number 3 is also with the roller support. Therefore, the vertical displacement is constant. Therefore, my V3 is equal to 0. Therefore, in the equilibrium condition, V1 theta 1 it is related to first row first column, and theta 1 is related to second row second column. I need to eliminate. V2 is related to third row third column, that I need to eliminate. And similarly, V3 is nothing but it is fifth row fifth column, that is what I need to eliminate. So this is what substituting the values of F1 M1 here, all the force matrix values are substituted. Now I'll do the elimination. So this is what my elimination: first row first column, second row second column, this is my third row third column, and this is what my fifth row fifth column. So these are the rows and columns I eliminated. After eliminated, I left out with 10 to 8 into 10 to the power of 3 outside as it is 250, and this is 50 and this is 100. So this is what left out, that is I have taken along with theta 2 theta 3. These are the two unknowns left out. Then minus 25 into 10 to the power of 3 and plus 50 into 10 to the power of 3, that is what left out. So in the next step, I need to open that matrix. I need to multiply that matrix. So 8 into 10 to the power of 3 into 200 into theta 2 plus 8 into 10 to the power of 3 into 50 into theta 3 is equal to minus 25 into 10 to the power of 3. That is what my first equation. Similarly, when I multiply for the second row, I will get the second equation. So this is what the two equations I am going to get. When I solve these two equations, I will get the values for theta 2 and theta 3. So solving these two simultaneous equations, I will get theta 2 as minus 0.0357 radians and theta 3 is plus 0.0804 radians. So these are the two slopes which are there at node number 2 and 3. Then in the second question, he has asked you to calculate what is the moment and the shear force. Let us calculate the moment first. So when you are calculating the moment at element 1, let us start from the left hand side. When x is equal to 0, that is my theta value is minus 1. So I know the moment equation. So this is what my moment equation. In this equation, wherever zeta, I need to substitute minus 1. Then outside ei divided by L square, I know all these values. When I substitute and when I do the simplification, here I need to substitute the values of displacement associated with the first element, that is v1 theta 1, v2 theta 2, v1 theta 1, v2. These are the three displacements which are 0. Theta 2 just now I calculated, that value I am going to substitute here. So after simplification, I'll get the value of m2 is 14.28 kilonewton meter. This is what the moment which is there in the first element on the left hand side where x is equal to 0. Similarly, on the first element on the right hand side where x is equal to 5 meter, there I need to calculate what is the value of moment, and that value of moment where I need to substitute the values of zeta as plus 1. So I know the once again moment equation. This is what my moment equation or moment matrix. So wherever zeta, I need to substitute plus 1. Then once again ei divided by L square value I have substituted. Then once again v1 theta 1 v2, these are the three displacements are 0 and left out with theta 2, that is what we have calculated, that I have substituted here. And after simplification, I'll get the value of m as minus 28.56 kilonewton meter. Now I need to do same thing for the second element. So when I start the second element, there x is equal to 5 meter, second element there it becomes zeta is equal to minus 1. Therefore, in the moment equation, now once again moment equation, please remember I need to substitute the 4 displacement associated with the second element, because now I am calculating the moment in the second element. The 4 displacement associated with the second element is v2 theta 2, v3 theta 3, that is what I have substituted here. In the same way, the value of ei and L square I have substituted, and wherever zeta, there I have substituted value as minus 1. So that is what I have done here. Now v2 is 0, theta 2 I have a value, v3 is 0 and I have a value for theta 3, that is what I have substituted. And after simplification, I'll get the value of m as 3.6 kilonewton meter. So that is what the value of m at the beginning of the second element. Similarly, I need to do the moment calculation at the end of the element where x is equal to 10 meter. There my value of zeta is plus 1. So once again, this is what my moment equation, and the 4 displacement associated with that element I need to consider. Therefore, in this equation, wherever zeta, I need to substitute as plus 1, and v2 is 0, theta 2 is I have value that I have substituted. Similarly, v3 is 0 and theta 3 I have value that I have substituted here. Then after simplification, I will get the value of m as 50.04 kilonewton meter. So this is the moment value which is there at the end of the beam where x is equal to 10 meter. Similarly, now I need to calculate the shear force. Now shear force will be calculated for the entire element. So this is the equation, or this is the matrix. As I am calculating the shear force for the first element, I need to consider once again the displacement associated with the first element. V1, theta 1, V2 are 0. Theta 2, I have value of minus 0.0357. Then EI LE cube is there now in the shear force. So that is a solved. And anyhow, this EI divided by LE cube, this is the common term which is there in the stiffness matrix, same thing. So that value we already calculated, that is 8 into 10 to the power of 3. Then first three terms are 0, then it is 30 into this value. So that is value I have taken. Therefore, my shear force in the first element is minus 8.56 kilonewton. Similarly, I need to calculate the shear force in the second element. So this is what my shear force matrix for the second element. Please remember, I need to consider the displacement associated with the second element, that is V2 theta 2, V3 theta 3. Then after substituting all the values here, now I'll get the value for theta 2 and theta 3. Those are the two values are substituted, remaining I made it 0. Then after doing this matrix multiplication and simplifying, I'll get the F value is 107.28 kilonewton. This is what my shear force value. Then the third question what he has asked you to calculate is the maximum deflection at the midspan of the first portion of the beam where it is carrying a UDL of 12 kilonewton meter. So I know the equation. With the help of shear function I need to consider. So let us substitute the value of N1, N2, N3, N4 in the V equation. Then I know at the midspan the maximum deflection will be there when UDL is subjected in the beam. So there my value of zeta is 0. So when I substitute the value of zeta in the above equation, and after simplification I'll get the Vmax is 0.02231 meter. So that is what the deflection which is there in the first portion of the beam because of the 12 kilonewton meter UDL. Similarly, he has asked you to calculate what is the maximum deflection where the beam is carrying 24 kilonewton meter UDL. So once again I'll consider same equation, but once again when I'm calculating the deflection at the second portion for the beam, there I need to consider, this should be second portion of the beam. Instead of second, it is typed as first. But there we need to consider the force displacement associated with the uh, second element, that is V2 theta 2, V3 theta 3. That is what I need to consider. Now I need to, along with that, I need to substitute the value of N1, N2, N3, N4. That is what I have done. Once again I am calculating at the midspan of that second portion of the beam where my value of theta is 0. When I substitute that and after simplification I'll get the Vmax is minus 0.02794 meter. So this is the value of Vmax in the second portion of the beam where it is carrying 24 kilonewton meter UDL load. Then finally he has asked you to calculate the reaction. So I have totally 3 vertical reactions and 1 moment reaction. So totally 4 reactions, because if you remember in elimination method we have removed we are eliminated the 4 rows. Therefore we are going to get the 4 reactions in that 3 vertical reactions and 1 moment reaction. First eliminated row, if you consider, you will get 1 vertical reaction which is there at node number 1. So that is what I have done here. When I consider the first eliminated row, I will get R1, that is vertical reaction, where I need to substitute the values of V1 theta 1, V2 theta 2, V3 theta 3, where I have only value for theta 2 and theta 3. That is what I have substituted. After opening this matrix, or when I do the matrix multiplication, I will get this equation. When I solve this, anyhow, I have this entire first eliminated row will be equal to F1. When I take that F1 to the left hand side, it will become minus of minus plus value. Therefore, after solving this, the entire reaction will be 21.43 kilonewton. Similarly, when I consider the second eliminated row, I'll get the moment reaction which is there at the fixed end. These are the second eliminated row values. Similarly, I need to substitute all the 6 displacements. Then that will be equal to M1, that is applied moment, and that value is minus 25 kilonewton. But it is there on the right hand side. When I take it to the left hand side, minus of minus, it will become plus. So it is plus 25 kilonewton, or 25 into 10 to the power of 3. When I do the matrix multiplication and when I do the simplification, I will get the moment at the fixed end, which is 10.72 kilonewton meter. Now similarly, when I consider the third eliminated row, I'll get the value of R2. So that is what I have considered here. Same procedure. Second eliminated row values are this multiplied with 6 displacement. then that will be equal to F2. When I take that F2 to the LHS, so minus of minus, it will become a positive value of plus 90. And when I solve this, the total value of R2 is 109.296 kilonewton. That is the value. Then coming to the last eliminated row, that is fifth eliminated row, if I consider, I'll get the vertical reaction R3, which is there at the extreme right hand side roller support. So same thing, eliminated row values and 6 displacement, when I substitute, that will be equal to F3. When I once again take the F3 to the LHS, minus of minus, it will become plus 60 kilonewton. When I simplify this, I am going to get the R3 value as 49.272 kilonewton. That is what my reaction which is there at the extreme roller support on the right hand side. This is how you need to solve the problem. Thank you for watching.